Hello everyone, and welcome. I'm excited to kick off today's presentation on vector algebra. Today, we'll explore the fundamental concepts of vectors, how they work, and why they are so important in various fields. We'll cover the basics, some key operations, and see how vectors can be applied in real-world situations. So let's get started and dive into the fascinating world of vector algebra. Now let's take a quick overview of what we'll cover in this session. We start with the learning outcomes, so you'll know what to expect by the end. Then, we'll look at the outline of the presentation, giving you a roadmap of the topics. Moving forward, we'll explore the types of vectors, which are fundamental to understanding the subject. Next, we'll delve into the magnitude of a vector, a key concept in quantifying vectors. We'll then examine scalar multiplication and the resulting scalar products, helping us understand how vectors scale and interact. After that, we'll discuss the vector laws for addition and subtraction, essential for combining vectors accurately. The fundamentals of vectors will be introduced to build a solid foundation. We'll also explore the unit vector, which simplifies vector representation. Then, we'll look at the angle between two vectors, crucial for understanding their directional relationship. Following that, we'll analyze the vector cross product, a powerful tool in vector calculus. We'll proceed with examples to illustrate these concepts, including example 5, 6, 7, 8, 9, 10, and 11, providing practical applications. We'll also work through exercises and correction from the previous lecture to reinforce your understanding. Then, we'll examine vector, cross, products of vectors, and the resultant of vectors, further deepening our grasp. Finally, we'll conclude with some quiz questions from April 19, 2021, and a thank you to wrap up the session. Throughout, I'll connect these points to the overall theme of mastering vector concepts for a strong mathematical foundation. Let's explore how the cross product is used in various applications. It helps us define angular velocity, which is essential in understanding how objects rotate. Additionally, the cross product plays a crucial role in analyzing the motion of charged particles within electromagnetic fields, linking physics and mathematics seamlessly. We also see its importance in geometrical applications, such as finding areas and orientations of vectors in space. Moving on, the dot product is another fundamental operation. It allows us to define and calculate important physical quantities like work, projections, and angles between vectors. It's a powerful tool for translating geometric ideas into measurable physical concepts. Lastly, we'll look at vectors in the plane. Understanding how vectors behave in 2 dimensions is key for many real-world problems and helps us develop a solid foundation for more complex analyses. By the end of this topic, you should be able to explain these key points clearly, connect their significance to the broader themes of the presentation, and appreciate how these vector operations underpin many concepts in physics and mathematics. Let's take a closer look at this first content slide, which is all about the introduction. Here, I want to emphasize that this part sets the stage for everything that follows. We'll explore the key points thoroughly, but in a way that feels natural and conversational. The goal is to highlight the most important concepts so they resonate with you. And as we go along, I'll make sure to connect these ideas to the overall theme of the presentation, helping to build a clear and cohesive understanding. Think of this slide as laying the foundation for the insights and details that are coming up next. Let's start by understanding what a scalar is. A scalar is a quantity that has magnitude, which means how much or how big, but it doesn't have any direction. For example, if I say I am traveling at a speed of 10 kilometers per hour, that 10 km/h is a scalar. It tells us how fast I'm going, but it doesn't tell us which way I'm heading. Now, this is different from a vector, which we'll explore in more detail later. The key thing to remember here is that scalars give us the size or amount of something, but they don't specify any directional information. Understanding scalars is fundamental because they are part of the basic building blocks in the study of physics and vectors. They help us quantify many everyday quantities without worrying about direction, making things simpler when direction isn't important for the context. In the broader theme of this presentation, Recognizing what scalars are helps us distinguish them from vectors. And that's essential for analyzing and solving many real-world problems involving motion, forces, and other physical phenomena. Let's talk about what a vector is. A vector is a quantity that has two important characteristics: magnitude and direction. Magnitude refers to the size or amount of something, while direction indicates which way it's headed. For example, imagine you're moving at a speed of 20 kilometers per hour, but not just in any direction, say, at 20 degrees. That combination of speed and direction is what makes it a vector. Understanding vectors is essential because many physical quantities, like force, velocity, and acceleration, are vectors. They help us describe not just how much, but also where something is going. This concept is fundamental as we explore more complex physical phenomena and their mathematical representations. Let's dive into the concept of the magnitude of a vector. The magnitude essentially tells us how long or how strong the vector is. Think of it as the length of the arrow in a graph, indicating the size or extent of the vector. Now, moving on to the illustration of vectors, we can see how they are represented in both 2D and 3D graphs. In 2D, the vector is shown with an arrow pointing from the origin to a specific point, while in 3D, it extends into the third dimension, giving us a more comprehensive view of its direction and magnitude. Next, we'll explore the different types of vectors. There are various kinds, such as unit vectors, which have a magnitude of 1, and zero vectors, which have no direction at all. Each type plays a unique role in our understanding of vector operations and applications. Finally, we'll look at diagrams and notations. Visual representations help clarify the properties and relationships of vectors, and proper notation ensures we're communicating about them accurately and clearly in our work and studies. Connecting all these points, understanding the magnitude and types of vectors, along with how we represent them visually, is fundamental to mastering vector concepts and applying them effectively across different fields. Now, let's move on to the concept of the resultant of vectors. This is essentially the single vector that represents the combined effect of two or more vectors. It's like when you're walking diagonally across a field. The resultant vector points directly from your starting point to your ending point, capturing the overall displacement. Next, we have the unit vector. Think of a unit vector as a vector with a length of 1. It's very useful because it shows direction without emphasizing magnitude. We often use unit vectors to specify directions in space, making calculations and understanding vector relationships much clearer. Then we'll touch on operations on vectors. These include addition, subtraction, and scalar multiplication. These operations are fundamental because they allow us to combine vectors, find differences, or scale them up or down, which is essential in many applications like physics and engineering. Finally, I want to mention that these topics are building blocks for more advanced concepts. As we continue, we'll see how understanding vectors helps explain real-world phenomena and solve complex problems more effectively. Now, moving on to the different types of vector products, let's start with the cross product. This is a way to multiply two vectors that results in a third vector, which is perpendicular to the plane containing the original vectors. It's especially useful in physics and engineering when dealing with torque or rotational forces. Next, we have the scalar or dot product. This product gives us a single number, or scalar, that reflects how much two vectors are pointing in the same direction. It's a handy tool for finding angles between vectors or projecting one vector onto another. Both of these products are fundamental in understanding how vectors interact in space, and they tie directly into the overall theme of exploring vector operations and their applications. So, grasping the differences and uses of these products is essential as we delve deeper into vector mathematics. Now, let's take a closer look at the tail of a vector. Think of it as the starting point or the origin from which the vector is drawn. When we talk about an example, it helps us visualize how a vector is represented in space. Next, we have vector notation, which is simply a way to write vectors clearly and consistently, often using arrows or bold letters. This notation is crucial because it allows us to communicate vector quantities precisely. Moving on, the direction of a vector is one of its most important features. It tells us where the vector is pointing in space, which is essential for understanding how it influences other quantities or systems. The head of the vector is the endpoint, the tip that shows the vector's final position from its tail. Visualizing the head helps us understand the vector's overall placement and how it relates to other vectors. Magnitude is the length of the vector, indicating how large or strong it is. It's like the size or intensity of the vector quantity. Recognizing the magnitude alongside the direction gives us a complete picture of the vector's effect. Together, these elements, tail, vector notation, direction, head, and magnitude, form the foundation of understanding vectors. They are the building blocks that help us analyze and interpret vector quantities in various applications. Let's take a closer look at some examples of vectors. As you can see here, vectors can be represented in various ways depending on their context. Moving on to the next point, we'll explore the different types of vectors. Understanding these types is crucial because it helps us grasp how vectors are used across different fields and applications. Recognizing the distinctions between these types allows us to better analyze and solve problems involving directions and magnitudes. So, as we go through this section, keep in mind that the variety of vectors reflects their versatility and importance in both theoretical and practical scenarios. Let's now talk about scalar multiplication. This concept is fundamental in understanding how vectors work. Essentially, when we multiply a vector by a scalar, we're scaling it, either stretching or shrinking it. The scalar is just a number, and it tells us how much to change the size of the vector. Importantly, the direction of the vector stays the same if the scalar is positive, but if the scalar is negative, the vector flips direction. This operation helps us see how vectors can be manipulated and used in different contexts, like in physics for force or in computer graphics for transformations. Overall, scalar multiplication is one of the basic building blocks for working with vectors and understanding their behavior in various applications. All right, let's take a moment to review some corrections from the previous lecture. As we discussed, it's important to clarify a few key points to deepen our understanding. First, I want to emphasize that accuracy in our foundational concepts is crucial for building more advanced ideas later on. We might have touched on some details that need refining, so I encourage you to revisit those sections. Remember, connecting these corrections to our overall theme helps us see the bigger picture, how each piece fits into the whole. By making these adjustments, we ensure that our knowledge remains solid and reliable. So, let's keep this in mind as we move forward, always aiming to refine and improve our understanding. Let's talk about the angle between two vectors. This is a fundamental concept because it helps us understand how vectors relate to each other in space. When we talk about the angle, we're essentially measuring how much one vector is rotated relative to the other. If the vectors point in the same direction, the angle is 0 degrees, meaning they are aligned. If they point in exactly opposite directions, the angle is 180 degrees, and if they're perpendicular, the angle is 90 degrees. Understanding this angle is crucial because it tells us about the similarity or difference in direction between vectors. We often calculate this angle using the dot product, which relates directly to the cosine of the angle. By doing so, we connect the geometric intuition to an algebraic calculation. This concept ties back to our overall theme of understanding vector relationships and their applications, whether in physics, engineering, or computer graphics. Recognizing the angle between vectors allows us to analyze directional data effectively, making it a key tool in many fields. Now, let's move on to calculating the area of this parallelogram, which is formed by the vectors p and q. The key idea here is that the area is given by the magnitude of the cross product of these two vectors. So, first, we'll find the cross product times q. Remember, the cross product essentially gives us a vector perpendicular to both p and q, and its magnitude corresponds to the area of the parallelogram. Let's compute the cross product component-wise. For the x component, we'll take the determinant of the y and z components and similarly for the other components. Once we've got the cross-product vector, we'll find its magnitude by taking the square root of the sum of the squares of its components. This calculation ties back to the overall theme of understanding three-dimensional shapes through vectors. It illustrates how vector operations like the cross product help us find geometric quantities, such as area, in space. So, let's work through these steps carefully to see how the math unfolds. Thank you so much for your time and attention today. I really appreciate the opportunity to share these insights with you. Throughout this presentation, we've covered key concepts and strategies that I believe can make a real difference in your work. Remember, the ideas we discussed are all connected by the overarching goal of improving efficiency and achieving better results. If you take away one thing, let it be the importance of applying these principles thoughtfully and consistently. I'm excited to see how you will implement what you've learned and the positive impact it will have. Once again, thank you for being here and for your engagement. I look forward to connecting again soon.